How symbols work and why we need them. My name is Anders. I work at Asenium down in Oslo, here in Norway. We are a startup designing a new and more efficient general-purpose CPU, which I think is pretty cool. Started there a few months ago. I mainly work on our simulator, so we're simulating this CPU and doing performance modeling and stuff. So I mainly write C++ all day these days, which is cool. I also run this website called cppquiz.org. It's a C++ quiz, and if you're into that kind of thing, there will be a C++ quiz at the party tonight. So please join if you like that kind of stuff, just having some fun with the language. If you're not into that kind of stuff, then you can still please come to the party, just don't join the quiz. Of course, when you have a talk, you have to plug your book. So I have this book coming out on pragmatic programmers in not too long. The cover was ready last night. So if you're into like figuring out how stuff works under the hood, I think there's a lot of cool details in this one. Right, we are going to talk about how symbols work and why we need them. And we're going to talk about static versus dynamic symbols, binding versus visibility, and how that relates to the concept of linkage that we have in C and C++. Linking, a bit about that. Weak symbols, what are those? Why do we have them? How symbols work with templates, inline variables. Where do these symbols exist? And how do you view them? Why do I have 3 symbol tables? Can I strip some of these symbols? Like, what happens if I do that? And who gets a symbol? Like, which things do you really need symbols for? And why do we want to learn about these things? The most obvious thing is if you're investigating some linker errors. So that can be simple stuff like undefined reference to some symbol, or like you have a duplicate of some symbol. Or it can be a lot more intricate, where you actually manage to introduce a duplicate of a symbol, and then sometimes this code path reaches that one, and the other code path reaches that one, and like you have to debug this and maybe actually re-architect your software a bit to fix it. Or you could be leaking symbols from your libraries to your users, and they could get some seg faults, and all sorts of interesting stuff. That's a lot easier to debug once you know these things. So it's interesting if you're consuming libraries. And it's more interesting if you're shipping binaries. So especially if you're shipping libraries, this is useful to know, but also actually if you're shipping executables. Personally, my favorite thing about this is just understanding how my binaries work. That's why I made this talk as well, because I didn't know a lot of this stuff, and it's just super interesting to figure out how stuff works, I think. Yeah, first a couple of things. Oh, yeah, so everything I say here is going to be about ELF symbols. So that's the executable and linkable format that we use on Linux. And then Windows has a bunch of similar things, but don't think that stuff from this talk directly applies on Windows, even though it's probably a useful background if you want to look into Windows later, but it's a different thing. Everything does apply both to C and C++, though. So I think it's cool this year that we have a strong C track. I'm mostly a C++ guy, but most of this stuff applies to both C and C++, except for some C++ specifics, like I'm going to mention templates, for instance. And yeah, one final note, if you have any questions about anything that's up on the slides, please ask right away so we can discuss it while we're on the topic. If you have more like, I would like to know more about this thing kind of questions, then please hold those to the end so we are sure to get through everything. And to figure out all of this stuff, before I start to like talk about in detail what a symbol is and how it works, I want to have a motivating example to motivate these questions, like what are symbols and what are symbols for? And my motivating example is this one. I have this values.c. That's a global variable called value with the value 42. It's constant initialized to 42. And then I have a getValue function, which just returns this value. So very simple stuff. I also have main.c, which just includes values.h to get to the declaration of getValue that we just assume exists somewhere. And main just calls getValue and returns. So this program should then just exit with 42. And in C and C++, you have this separate compilation model, right? So you can take all of your C files or CPP files and compile them completely independently of the others. So main.c, when I compile that, I can't see what's inside of values.c. Like everything, if you have enough cores, you could, in theory, compile your entire project in parallel, right? So the compiler is going to take main.c, and then it's going to just copy-paste values.h in here and compile that. And that's what we call a translation unit. So the C file with all the includes included and stuff, then that's a translation unit. And it's entirely independent of all of your other translation units when they're compiled. So these are going to get compiled into some object files that has some arbitrary bytes in them. So values.c turns into values.o, and there's a really big lag on the projector. That's very challenging, okay? I have to deal with that. Values.c turns into values.o, main.c turns into main.o. And then I've color-coded it a bit here, just trying to illustrate that there's some data, that's like the purple part, and some code, that's the green part. And these are not necessarily real bytes. This is just for illustration, showing that there's some data in here and there's some code in here. And then probably I have some library that I use as well. Maybe it's my library, maybe it's a third-party thing. But at least I have all of these object files that have been compiled. I have this library, and then I want to make an executable out of this. So we're still talking only about static linking here now. So I want to link an executable called the program from all of this stuff. So what the linker does then, it's going to take all of these purple data sections and just squash them together into one big data section in your executable. And it's going to take all of your machine code, which lives in what's called the text section. That's where the code goes. Take all of these and just squash them into one big text section in your program. And then you're done. You can run your program. But the thing here with the separate compilation model is that when I compile main.c into main.o, I don't actually know where get value is. Right? The compiler has to generate some code to jump over to wherever the get value function is. But I don't know that because I've only seen the declaration. I don't know where it is. So I can't know when I compile this where get value is. So if I have a look at values.o, this is still the same values.c here, I can dump it with a tool called objump. So objump is a useful tool to look at all sorts of stuff about your binaries. So one of the things I can do to look inside of values.o, the object file from values.c, is let's just dump the bytes in there. Let's see what's in there. Like this isn't a very useful tool when you're actually investigating stuff, but just for illustration, let's do objump-s to just list the contents of the sections. It starts by saying the file format is ELF64 x86-64. So that's just the ELF. That's a binary format we use on Linux, and it's on a 64-bit system here. And then it says the contents of the text section. So I mentioned the text section is where all your machine code goes. So these are the bytes that are going to be put on your CPU eventually. And I happen to know, well, it says the address here, and then I happen to know that 55 is push RBP, and C3 is ret, and that's the first and the last instruction in my function. So in the text section, you only have these bytes, just the bytes that go on the CPU, and no metadata or anything like that. In the data section, we have this 32-bit value, 2A. So 2A is hex for 42. So we have just these 4 bytes for this data. That's all that is in the data section. And just dumping the bytes, that's not the most useful way to look at an object file. So another tool I can use to look into my object file here, or another way to use objump is to pass it -d to get the disassembly. There's going to be a little bit of assembly in this talk, but you don't need to know any of that. I have a link at the end to a talk about like more an introduction to assembly for these kinds of purposes, for like calling functions and stuff like that. So again, it has this header saying it's an ELF64 thing, and this is the text section. And then it goes, here are the instructions in values.o. So we have the same bytes that we saw, like from 55 to C3. These are all the bytes. And it's grouped it by instruction. And then it's disassembled it. So 55 is push RBP. And then like we have these instructions here. So here are the actual bytes inside of values.o. And here is like what that would be in assembly. There's no assembly in the object file. It's just objump translating it so I can read what's going on in here. And object is also nice enough to show me that, well, this is the getValue function. But that's not in here. This is just a machine code, but still objump is able to show me that, well, these bytes came from the getValue function. So then it's probably obvious by now that we need some sort of table of symbols somewhere for objump to be able to show me this, and for the linker to figure stuff out. We need to have some symbols to find things. And indeed, there's a symbol table, and if I say to objump -t, that means please show me the symbol table. What are the symbols that are in this object file? Again, it has this header saying, here's the symbol table. And this is easier to read from the right to the left. So it starts saying, I have a object called, a symbol called value. And then it says it's 4 bytes big. It lives in the .data section. It's an O, that means it's an object as opposed to a function. It's global, I'll get back to what that means. And it's at offset 0. And it also says, well, there's this getValue function that we saw. It's C in hex, bytes big. It's in the .text section where all the machine code goes. It's an F for function. It's also global, and it's also at offset 0. So these offsets are relative to the section. So value is the first and actually only symbol in the data section, and getValue is the first and only symbol in the text section. But who uses objump to look at symbols? A couple, actually. Yeah, that's like 10% of the room. That's more than I expected. What do the rest of us use? We use NM. So I can list the symbols with NM as well, and then it shows me getValue has a capital T, meaning it's in the text section, and value has a capital D, meaning it's in the data section. So NM is also a handy tool to just list the symbols that are in an object file, and then you can see a bit of information about them. I can also run objump to list the symbols in main.o, which is the thing that calls this getIt function, or the getValue function. And it says, well, here's main, it's in the text section, it's F for function, and then it says, I also have a symbol called getValue, but it's undefined. All right, so when I compile main, the compiler figured out there's a call to a getValue here, but I don't define that symbol. I only require that symbol to be defined. So I get an undefined symbol for this in main.o that the linker can then resolve later. And yeah, if I run nm on values.o, I see I have this u, undefined symbol getValue, and t for main, it's in the text section. So then we've seen we have the data section for the data, the text section for the text, and then we have talked about there's a symbol table somewhere. So how many sections are there in this object file? I have another tool called readelf, which can list a bunch of metadata as well. And yeah, I give it -s to show me all the section headers, and W, just like always use W when you use readelf, because then you'll have the wide output and it doesn't get mangled, which is annoying. And readelf tells me there are actually 20 section headers. So in my values.o, with just this single global variable in the function, I have 20 different sections. And then it lists all of them, and we can see down here that we have our text section with the code, the data section with our globals, and symtab. So that's a separate section that has these symbols, and these are just like pointers into the other section. So it's saying that you have value and getValue, and they are over here. So that's the metadata that's off in a separate section. Yeah, so we mentioned earlier, looking at this figure, that when the compiler is compiling main.c in isolation, it doesn't know where getValue is. Like, how can I generate a call to this function that I don't know where is? But the linker has the full picture. The linker is writing all of this stuff, right? So the linker knows, well, this section here, I'm going to write it over here, and this section here, I'm going to write over here. So the linker has the full picture when it's making the program. And then the linker can use the symbol table to find the offset. Like, I put values.o in here, and what's the offset of getValue? It's 0, so then it knows actually where it is. And yeah, so let's briefly then look at how does that work? How can the compiler not know, and then the linker can know, and then the linker can fix it? How does that work? That works with relocations. I'm gonna mention relocations briefly here. I had a talk 2 years ago about static linking and dynamic linking also, but going into a lot of details about relocations. So I'll have a link to that talk as well at the end. I again used objump-d to disassemble my main.o now because I'm gonna look at the call to get value and figure out how it works. So I'm dumping main.o this time. -r is to show the relocations, which is the thing that the compiler and the linker uses to communicate these things. And finally, I'm just saying -m intel because I want the intel assembly syntax, because that's what most people use these days, I think. Okay, so here's the disassembly of the text section. And then it goes a lot of stuff that we're not going to talk about now. And here's the call. So E8, that's the call opcode. So then when the CPU sees E8, it's going to like jump over here and call this function. And then what's the address we're going to call? 0. Like the compiler just went, I have no idea where this function is going to be, so I'll just put some zeros and I give up. And then the compiler also generates a note to the linker to say, like, hey, can you please fix this up later? I just put zeros here for now, and then the compiler has added a relocation. And again, the relocations are off in yet another section. This like machine code is still just machine code. There's nothing magic in here. But off somewhere else is this relocation information, and objump is just inlining that information here because it's easier for me to see. So it has said that at address A, please put in the value of get value. So this is byte number 9. This is byte number A. So the linker can then just figure out where it put get value and then just fill it in here. So the linker doesn't need to understand machine code or assembly code or like anything like that. The linker just knows, well, at this address, I need to put the address of where get value eventually ended up. So during linking, the linker just loops over the relocation table in main.o, finds all the missing symbols, and then it looks in the symbol table for values.o and finds, okay, what's the offset of get it? And I know where I'm going to write this section that I got from values.o, where in the executable does the stuff from values.o end up. So then I can add that the offset to that, compute the final address of get value, and just fill it in at this address. And it's going to be a relative address, but that's not very important right now. Yeah, and again, objump is inlining this information, even though it's actually off in some other section. It's not here in the text section. I can then disassemble my final executable. So after linking the program, now it's just the executable. Everything has been linked in. Everything is done. I can objump that again to show the disassembly. And here's the main function. And here we can see this call instruction, the E8 for the call. And now the linker has put in the final address. So the actual distance it has to jump to get the get value has now been filled in. And the relocation is also gone. We can also note that the main function no longer is at offset 0. So when you link the final executable, lots of other stuff has been added here. So main now starts at offset 606 in the text section. So other things has been added here as well. So what if there were no symbols? Like, I'm trying to figure out why we need these symbols. What happens if you don't have any symbols? So I'm linking this program. I don't remember how to call the linker, so I just use GCC, gcc-o, the program, values.o and main.o, just to link this into an executable. And you remember main calls get value, and get value returns this global, which has the value 42. So when I run my program, there's like no tricks here. It just exits with 42 as we expected. So that worked fine. And as we saw, this worked fine because when I list the symbols in values.o, we have the symbol for get value, so that the linker knows where get value is when it's linking the executable. But I can use this tool called strip, and strip will just remove all the symbols. So just the code is exactly the same. It doesn't change anything. Like the symbol is different from the actual thing in the code, right? The function is a thing in the machine code. A symbol is just a pointer somewhere in some other section. And strip is just going to throw away that entire symbol table, so there are no symbols anymore. So if I do that, and then I run nm again on values.o to list the symbols, and nm tells me there are no symbols in here. So if I try to link again, just to make this executable out of my 2 object files, I'm going to get this like you've maybe seen sometimes before. the linker complains that there's an undefined reference to get value because the symbol table isn't there. So then you can't link to it. And now you kind of understand a bit more how is the linker able to like find these things and complain if they're not there. So the story so far from the introduction is that we have a separate compilation model. So all of your C and CPP files are compiled in isolation. They can't look into the other ones. We've seen that we have sections like data for the globals, text for the code, sim tab for the symbols, and so on. And there are at least 20 of them. Text only has machine code, so like no metadata, just the code that goes on your CPU. Data only has the global data. And then .sim tab has symbols pointing to each of these functions and objects in the other sections. We also saw that the compiler creates relocations for the linker. There's these little notes for the linker to fix up the right addresses when linking, and that these live off in yet a different section. Yeah, the linker fills those in. And if you don't have symbols, well, then you can't link. That's it for the intro. Next topic is linkage. In C and C++, we have this concept of linkage. And I have done something here. I have this get value that we've seen like in our example so far, but I've introduced this helper function. So get value calls helper, and helper then returns the value, and then this gets returned from get value eventually. And I've made helper static. So what does it mean if I put static in front of my function here? It's local to this file. That's correct. So static here gives this internal linkage. That means only this translation unit, only this C file can call this function. It's invisible outside. So helper has internal linkage, and value and get value have external linkage, meaning you can link to this from the outside. No one else is allowed to use this helper function. And if you're more used to C++, maybe you have anonymous namespaces that you tend to use instead. That's the same thing. Then you get internal linkage. So no one else can see this after it's been compiled. It's invisible. So if I list this, we can see that like we saw before, get value and value, they have capital T, capital D for text section and data section. And helper has lowercase t. And this lowercase means internal linkage. So get value and helper have external linkage, so they get capital letters. And helper has internal linkage, so it gets this lowercase t. And linkage, that's just a language thing. Like C and C++ in their standards just say, here's how a linkage works. And then just Linux and ELF have to support that in some way. Like we have to have some feature that provides that functionality of the languages. But ELF doesn't have like a linkage concept really. ELF has another thing called binding. So binding is the mechanism in ELF that you use to implement this language feature of linkage. So the binding is kind of very related here in that value and get value have external linkage, so they get global binding. So like globally available. Whereas helper has internal linkage and then has local binding. So it's local to this file. It's not available outside of it when you link later. Yes, and then in main.c, I also needed a helper, because if someone forgets to pass the right command line arguments, I want to print this usage string. So I made a helper function to print the usage string. And then I have two helper functions. And like normally that doesn't work when you link, but since both of these have internal linkage, they have local binding in ELF. So when the linker links these, it goes, well, there are two helper functions, but that's fine, because those are just internal to those things. I can't link to them between files anyway, so just name them whatever you want. I don't mind if you have a collision. And the same is with an anonymous namespace. You can have like a function f in all of your translation units, and that's going to be fine. And this separate compilation and linking model is why you can't have your definitions in your headers. So if I were to move up to values.h, I put now the definition of value here in values.h. I put the body here, so we have the definition of get value up in the header file. And then I include this header in two C files. Now both values.o and main.o are going to have the definitions of value and of get value. So if I try to link those object files later, it's going to say, well, there's multiple definitions of both value and get value here, so I can't link this. Like, which one am I going to use? I have two, you're only allowed to have one. So yeah, then we kind of see how the linker is able to figure out this problem and how it's able to give you this error message. So what do we do? The classical solution here in C is that you have to just declare them in the header file and define them in some C file. You put extern on this one, and then you remove the body from get value. Now these are only declarations, and then only values.c actually define this. So then only values.o are going to have the definitions, and linking is going to work fine. And in main.o, then you're going to have like an undefined symbol for get value, and the linker will be able to figure that out. C++ has some additional challenges with header files. In C, it's pretty simple. You just move these things down. But in C++, you have a couple of extra challenges. Just like a quick question. Who uses C++? Most of the people. I've tried to keep this a bit language agnostic since we have this really cool C track this year. But here's some C++ stuff. So one thing you can do in C++ is that your structs, they are now called classes, and they can have functions in them. And I can put the definition of get value inside of this definition of some class, or I can like put it down in some header file going some class : get value and just have the declaration. But I'm allowed to put the member function inside of the class definition. So when I include this header file in many of my CPP files, I'm now going to have the definition of get value in all of my my object files. So that shouldn't work, right, when you link this stuff. Another thing I have in C++ is templates. So if I have this function template called getValue, I can instantiate getValue for int in many of my CPP files, and then I'll have duplicates. But I need to put the definition here in the header file, because otherwise, how can my CPP files instantiate this template if it can't see the entire definition of the template? So I have to put it up here, and then I have to get multiple definitions of getValue of int if I use that in many CPP files. So if I, in some CPP file, I use this, so I use getValue of int here, and then I just create an object of some class and call this member function. Now I get code for these generated and symbols for this generated in this file. So how does that work? Let's run nm again, and now we're in C++, so I pass -c to demangle the names, so we get the proper C++ names and not like the weird like mangled names. And then we can see that use it, which is a normal function. It's still capital T, is in the text section, global binding. But get value, these two get value functions now have a W. And the W is a new thing. Like we've seen, global binding, it's available everywhere. Local binding, it's internal to this file. Weak binding means it's kind of like global, but you can have many of them. So if I instantiate this function template in 11 object files, the linker is going to discard 10 of them and just make sure there's just one left, and everyone uses that single one. So that's how that's supported on ELF, because again, this is just a rule in C++, right? We have a thing called the one definition rule. And the one definition rule says you're only allowed to have one of each thing in your program, each function, each global, and so on. You can only have one definition, except for templates and a few things where you need to allow to have many, because otherwise things wouldn't work. So then it says you can have many of these, and it's not a violation of the ODR one definition rule. It's not an ODR violation. You're allowed to have these, but they had better be the same. Imagine that I use this get value of int in several of my files, and there's an if-def in here. So it goes if-def something something, return 1, else return 2. And then I instantiate this in many CPP files, but only in a few of them do I define this, they set this define. So for some of them, the if-def is true, and for some of them, the if-def is false. So some of these instantiations return 1, and the other return 2. That's an ODR violation. You're not allowed to have that. If you have many copies of the same thing, they must be exactly the same. Otherwise, you have an ODR violation, and that's undefined behavior. So you can't have that. Yeah, and also one more thing about weak symbols, like if I don't use this template, or if I don't use this member function, I don't actually get them instantiated. then the compiler will just go, well, if you're not using them, I won't bother emitting code and symbols for these, because anyone else who's using them will also have emitted code for them. So I don't need to have these symbols. So if you ever like look at their symbols and like, why is there no symbol here for something in up here? It's like, okay, if you don't use it, the compiler just didn't bother. We didn't say anything about weak symbols to C++, right? We just used the language like you're supposed to use it, and we didn't say anything like this is weak, so we can have many. We just like that's the compiler just handle it, and the implementation just goes, well, we can use weak binding for this in ELF to support this language concept. But I can also use weak symbols manually if I want. And this is not standard. This is just like a Linux-only thing. But I can use weak symbols myself if I want. One way I could choose to use weak symbols is if I complicate my library a bit. This library to get the value 42, I'm going to complicate it a bit. So the way you get the value now is that you load a resource, and then you get the value from that resource. So in my header file, I declare load resource, and in my C file here, I give you a definition for load resource. And this resource loader is just doing something to get the resource. Like it reads a file, connects to a database, or I don't know, like something to get this value. And then my user will just get the resource, just calls the get resource function. Now I have a resource pointer that comes from somewhere, and I can return the value from this resource. So my resource here is just like an abstract thing that gives you the value 42. And I have an implementation here of this resource loader in my C file. So if I call that, I get the resource somehow. But what if I want the user to be able to override this? Yes, my default implementation uses a database, and the user should be allowed to use a file. Or the default implementation computes this on CUDA, but the user should be allowed to do this on OpenCL, or I don't know. How do I do that? Well, then I can actually manually mark this symbol as weak. So I can put attribute weak in front of my declaration of this function, and now this is a weak symbol. And then my user can also provide a definition for load resource. So now I have a weak one, and they have a normal global symbol. So they don't put attribute weak here. And then the rule is that if the linker sees multiple, like one or many weak definitions and one global definition, it's going to pick the global definition and discard all the weak ones. So now when the user links their application, mine just gets thrown away by the linker, and instead it's getting overridden by this global symbol from the user. But you're still allowed to only have one of the global ones. So if I have many of these ones, then that's going to be a multiple symbol definition and an error again. But yeah, so this is how you can allow the users to override some functions and have a little kind of plug-in system like this. But again, this is vendor-specific stuff, right? And now if I look at values.o and main.o, look at the symbols in those, I have then in values.o, I have a weak symbol for load resource, and in main.o, I have a global symbol for load resource. So now this one is going to take precedence during linking. One final thing in C++ that is a bit like complicates things a little bit is inline variables. So we mentioned that you can't put your definitions in your header files. Well, as of C++ 17, you can put your definitions in your header files. If I just type inline in front here, I'm actually allowed to have this global value in the header file. I can include it in many object files. I get the definition of global value in all my object files, and then the linker is just going to disambiguate and just pick one of them. I can do the same with the static members as well. So I can have an inline thing here. Like previously, you always had to go in your CPP file and type some class : local value equals 2. But now you can put it in the header file, which is just convenient. Yeah, and then I just have a static member function as well, just to get this value. Now, as a user, I'm going to just, in my main function, I'll return the global, and I'll call this static member function, which eventually uses this inline variable. So how does that look? If I look at my my object file again, I do nm on main.o, again -c to demangle the names. Then we have main, regular, capital T, global linkage, global binding in the text section. And this member function, the W thing that we saw before, it's a weak symbol because I have a definition of a function in a class. It's going to end up in many of my object files. And then for these inline variables, we have a U. Now, that's a new thing. This is a unique symbol, and that's a GNU extension to ELF. That's just how GCC decides to do this stuff. And a unique symbol is the same for most practical purposes as a weak symbol. It just means you can have many, but the linker is going to pick one. You just pick a unique one. The only little difference is that you're not allowed to override this one. So you can't have a strong one that overrides all the unique ones. They have to be all unique. And then, yeah, the linker is just going to pick one. And then one little unfortunate thing here is that we saw earlier that we have the capital T, meaning global binding, text section, lowercase t, local binding. And we saw for data, you have the capital D for global and lowercase d for local binding. So you have the lowercase u for unique symbol, and then uppercase U for undefined symbol. Like, these are just completely unrelated. So yeah, that's like when you start learning like the capital is global and the not capital is local, then that only works for a while. Yeah, so just watch out for that. And then when I learned this stuff, I had some questions, and maybe you have some questions as well, because I thought the linker just copies sections. Like we saw in the first illustration, it takes like this entire section, puts it over here, takes this entire section, puts it over here. And it doesn't understand machine code. I also said that, so it can't really change the sections. It just like copies them verbatim over to the executable. But I also told you that the linker is going to remove these things, right? It's going to pick out the get values from all of your object files except one. So how can you do that when you can't modify the sections? And that's not possible. It can't pick those things out of the sections, but it's still managing to do this somehow. So how is it doing this? So I'm objumping main.o again, and I'm grepping for the text section. I'm listing all my sections here and just grepping for my text section. And here it is. Here's my text section with all my code. And here are also my text sections, a couple of new ones. So I have the text. This is not possible to demangle, unfortunately, but you have the text some class : get value section, and you have the text.get value of int section. So what the compiler actually does for all your weak symbols, all your function templates and stuff, it makes an entirely new text section just for that single function template to allow for the linker to throw it away later, because you can't chop out parts of the official text section or the large one with all the normal stuff. So it has to generate all of these extra text sections for all these things that can be removed later. Yeah, so this happens then for inline variables, for templates, and stuff like this. They all go in separate sections. So in summary, for binding, in C and C++, we have this language concept of external and internal linkage, and that's implemented on ELF with global and local binding. Then we have weak and unique binding as well to support things like anything that's defined in a header has like a weak or unique symbol. That's the intuition to take away. So that's like member functions that are defined inside of the class, function templates, inline variables, all of these things that you're allowed to define in your headers are implemented in this way. I can actually use attribute weak manually if I want to allow people to override my stuff. And we saw how the linker uses one section actually per weak and unique symbol in your files to be able to disambiguate later. Right, that was static linking. Next thing is a bit hairier, and that's dynamic linking. The C++ 20 standard is 1,826 pages long. Oops. I don't have a copy of the 23 one. It's probably even longer, but it's a pretty long document. And I don't know C very well, but that's probably also a quite long document. So how many pages do you have to cover this complicated topic of dynamic linking? Yeah, 0. There's nothing in these standards about dynamic linking. C and C++ do not know anything about dynamic linking. If you've heard ever about like dynamic linking, it's all made up. It doesn't exist for real. It's not a thing. Everything is vendor specific. And that leads to all sorts of interesting questions, especially around like the ODR things and yeah, the different discussion. So everything is vendor specific, and in this talk I'll only talk about how this is implemented on ELF. I'll have a short mention of Windows as well, just for some cross-platform niceness that you can use. But this is Linux ELF specific stuff. So we're going to use this example again, where we have values.c and other.c. So this used to be main.c, now it's just other.c, because these are now going to be part of my library. So I'm making a dynamic library here. So now these are two of the things that go into making my dynamic library. And there are many names for dynamic. So now I said dynamic library. The official term on Linux is dynamic shared object, or a DSO. And some people just say SO. Some people say shared libraries, dynamic libraries. A lot of people I hear say DLL, actually even on Linux, even though that's like a Windows thing, but like it's kind of the same thing. But a shared object is what I'm going to stick with for this talk. So everything we learned so far is exactly the same when you're linking. You're making the SO, right? Then everything, like all of the relocations, the binding, all of the stuff we looked at is still the same when I'm making this shared object. So everything still applies. But it does not apply to when I'm actually going to consume the shared object. Then that's when things start to get different. Because there's probably a lot of stuff that goes into my SO, and then I have a little bit of an API surface that I want to allow my users to use. And most of my stuff is probably internal stuff that I don't want them to like accidentally start using. If it's possible, even though it's not in a header file, someone is going to find out, oh, there's this function, it's very useful, I can use it, even though it's not in a header. And they're going to do it. And also, a bunch of this stuff might be secret, right? So I don't want to expose all of my secrets out of the SO, so I want to try to contain it a bit. And also, when I load an executable, that will then load all of my dependencies, all my other shared objects that depend on other shared objects. And as I load this, then the dynamic linker and loader will have to patch up like where are all the addresses in this SO and where are all the addresses in this SO. So there's some work that has to be done. So actually, you might even slow down dynamic linking and loading a little bit if you have too much stuff on your surface. So let's look at an example of internal and versus API things in an SO. Yeah. So here's one of the files that go into making my SO. I have an internal function that I don't want my users to use, and I have an API function that I do want my users to use. And then in a C file, I have the definitions. Internal function returns 1, and then the API function calls the internal function and just multiplies the value by 2. And if I then run nm on this, we've seen this many times, you get the capital T, it's global binding, it's in the text section, both of these functions. I can also run nm on the shared library itself. So after I made my dinlib.so, I can run nm on the final thing, the completed linked product, and I will see I also have global binding for API and internal functions. But I want to control so that my users can only call the API function, not the internal function. But I can't use binding for this because like this is just one C file. I probably have like 40 or 500 or whatever other C files, and some of them might need to use the internal function, right? So inside of my SO, all of my CPP or C files are allowed to call all this internal stuff. It's just on the surface, they should not be allowed to do that. So I can't change the binding. The binding has to be global so that all of my files inside of the SO can talk to each other and use functions from each other and be linked into this SO. So I need to control only what's available on the outside. And to do that, I use visibility. So visibility is a different thing from binding. Visibility is a different thing from binding, and binding is what we've seen a lot so far. It controls, can this symbol be used outside of the translation unit? When I statically link stuff, can they link to each other? So binding matters when I create my shared object. Visibility controls whether the symbol can eventually be used outside of the shared object. Can my users link to this? And that matters when you're linking to the library, not when you're making it. But C and C++ do not know anything about dynamic linking or visibility. And we saw previously that the linkage concepts in C and C++, that directly translates to binding. So that's nice, you have this language thing. But for dynamic linking, visibility, there is no such concept in the language. So everything is vendor specific. And on Linux, the way you solve this is that you put an attribute on your stuff saying this one has default or this one has hidden visibility. And default visibility means it's visible, and hidden visibility means it's hidden. You can't use it. And you can control that per thing, per symbol. You can put this attribute visibility default or hidden. And if you put attribute visibility default, then it's visible. If you put attribute default visibility hidden, it's going to be hidden. You can also just give a compiler option, and then it will apply to everything when you compile this file. So if I pass f visibility hidden, all the symbols in my file are going to get hidden visibility, and nothing can be used on the outside. And if I don't pass anything for f visibility, the default is to use default visibility. And it's a bit unfortunate that we have default means two things here, right? Default visibility is it's visible, and the default option for this one is this default. And not it's a bit so the default is the normal thing is that we get the default visibility. It's visible outside, and then I can override it and then if I want. On Windows, it's a bit weird because on Linux you just say here's the thing. This is you can link to it from the outside or not. On Windows it's a bit strange because when you declare your function on Windows for a DLL, you have to say DLL export, meaning it's going to be exported. That's the same as on Linux, that's fine. But then when you use the DLL, you have to put declspec DLL import. So when I call a normal function, I will put DLL import here, and it will make it a slight bit faster, apparently, to call stuff in DLL if you put declspec DLL import. So I'm not too sure about the details, but that's what you should do on Windows, apparently. But yeah, back to Linux. How do you control visibility? You use your build system. I happen to be using CMake here. So what I typically do is I have add library. I'm making a dynamic, making this dynlib, my shared object. And then I set the compiled options for dynlib, f visibility hidden. And now all of the source file that go into making dynlib will have f visibility hidden. So all of my symbols are hidden. No one can use anything in my library. Then in my header files, I can choose the stuff that actually goes into the API. I'll put attribute visibility default, and then only those things will be visible. So now my users can use API function, but not internal function. I could do it the other way around as well. I could have the default visibility be default visibility, and then put attributes visibility hidden on the stuff I want to hide. But I think it's better to do it this way because it's very easy to forget to hide stuff, right? You won't notice that you forgot to put this on half of your stuff. If you forget to expose some things, then, well, your tests are going to tell you that I can't link to the things in the API. So, and also, I would assume that most of the symbols in your SO are internal stuff. You just have a tiny subset that you expose, and it's just less typing if you don't need to decorate everything. And you don't want to type this stuff everywhere. So you make a macro like DSO export or just come up with a name, which means attribute visibility default. And then you just put this in front of your stuff. And only those things get exported. So, yeah, question? Yes, you can. I'll have an example for that a bit later. Yeah, so I'll have a quick mention of cross-platform here. Again, I don't know Windows very well, but I'm told you have to put DLL import when you use the thing and DLL export when you make the thing. And then the header file is often the same. You often use the same header file when you build your DLL as when you consume your DLL. So the function declaration has to say DLL export when you make the DLL and DLL import when you use the DLL. So how do you make the header file say two different things in two different scenarios? And you use if-defs for this. So this is a cross-platform DSO export definition that works both on Linux and Windows. So I say if I'm on Windows underscore Win32, if I'm on Windows, I have another thing. So I have this building DLL. So whenever I compile something that goes into the DLL, I pass this compiler option that's setting the building DLL thing again, then using my build system. So whenever I build stuff that goes into the DLL, building DLL is set. So now DSO export means DLL export. And if I'm not, if I'm just using this header file because I'm using the DLL, I have not set this one. And then it says, then it means the DLL import. That's how you can make that work. And if you're not on Windows, you just use this like more sensible thing, like at least to me, you just define it only when you build your SO. You just set, well, this one is visible to everyone. Right, so that's a cross-platform kind of trick you can do for this. If you're into shipping cross-platform dynamic libraries, which has a whole list of interesting problems. Yeah. So, excellent question. Like, can you see these things? And if you use nm on library.o, I can only see that, well, these have global binding in the text section. There's nothing about visibility here. And that confused me initially when I was trying to figure this stuff out, like what's the difference and like how to view it. readelf, if you pass -s to readelf, you can see the symbol table, and readelf has a lot more details here. So it's a bit nicer because you have, here's the binding, the thing that matters when you make the library, and here's the visibility. So they both have global binding, so they can call each other when you're inside of the SO, but on the outside, internal function is hidden, API function is default. I can also list the symbol table on my SO. So after linking the library.o and all of my thousands of other files into my shared object, I can list the symbols here. And now we see, oh, there's a new symbol table. So far we only seen symtab, but here's a new one called dinsym. And dinsym only has API function. There's global binding, default visibility, and the internal function is not even in that symbol table. But why? Why do I have two symbol tables? Because like all the info is in here, right? Everything is in the normal symbol table. So why do I like duplicate half of that information in another symbol table? And the reason for that is that syntab is used for static linking, the dinsym is used for dynamic linking, and I think I actually have, yes, I have a slide for this. Yeah, why not just put binding and visibility in one table? It's already actually in one table. It's in syntab, so why also have a dinsym? The thing is that the dynamic symbol table is needed at runtime. So when I load my executable and all of my SOs, the dynamic linker and loader has to patch up some of these addresses to call between the SOs. Yep, and then it's nice if that table is kind of small, doesn't take a lot of space in memory, and it's quick to look up and if it's a bit small. And if you care about size, there's also the strip tool that we saw briefly before that can strip away the symbol table. So after making my SO, I can run strip on the SO and strip away the static symbol table, which is the big one, which has everything. And then it can leave only dinsym, which only has this little subset of your symbols that go into your API. So now you have a smaller binary as well, which some people care about. And another reason to use strip is that it can add a bit of security by obscurity, right? So if I'm like a mediocre guy somewhere who wants to try to reverse my competitor, if the static symbol table is there, I can just put breakpoints on like all the like interesting looking stuff. I'll list all the symbols of this shared object, and I'll just put breakpoints on the encrypt stuff and the super secret function and stuff like that. So if that's stripped away, it raises the threshold a little bit. So like normal guys like me will give up, but like when the Chinese government is trying, they will probably be able to do it still, right? But a little bit of security by obscurity can be fine sometimes, right? But there are more symbol tables. There are at least 3 that I know about. Like there's also the debug table, right? So you have the static symbol table and the dynamic one. They just have, here's the name, it's there. That's all they have. So they're not too large. But the debug thing has all sorts of stuff, like which file did this come from? Well, and this instruction here came from that line in this source file, and like, lots of info. And again, if you care about size, you will, and also if you care about like a little bit of security by obscurity, you will strip away both the static symbol table and the debug info, so it's only the DINSym left, and you'll have a smaller binary. Yes. Now we talked about like what symbols are, why we need them, how they work and stuff. But last thing I want to mention here is like who gets a symbol? Like which things in your program need symbols, right? So let's play a little game of who gets a symbol. The first one is similar to what we've seen. You have a global variable and you have a function that's defined here. So which of these get a symbol? Both? Yeah. Objects, capital D, global binding in the data section, and the function capital T, the global binding in the text section. So you get symbols for both of these. What if I make them static? So now they have internal linkage. What changes then? Now I get these lowercase ones, because now they have internal linkage, they have local binding, so they can't be seen from the outside after you compile this stuff. So now they get the lowercase ones. And I put a question mark here, because if I actually use them, I get them. If I don't use them, the compiler will just not emit this code, because no one else will be able to link to it. You're not using it, so I would just won't emit code for this. And also, this is a debug build. And if I built this in release, I would probably get like constant folding and all this stuff. Everything would be inlined, and then again, this wouldn't be needed anymore in the binary. Then I have a function again, and this time the function takes a parameter called param, and it has a local variable called value. So which of these get symbols? Function, param, and value. Yep, function. Because the function is a thing in your program. It's like, here is the function. Everyone who calls this function needs to call that function. So they have to be able to link to it. They have to be able to find it. So we need a symbol. Param and value, like every time you call this function, you have a different instantiation of this function, and you get a stack frame somewhere. So like, where is param and value? Well, that changes. That depends on where you are in the stack. So it's not one thing, right? It's not the param for the entire program. There are many of these every time you call the function. And if it's a recursive function, you can have many instances of this function on the stack at one time. So these are not like a thing. So you can't link to them. They're not a singular thing. They don't need symbols, and you couldn't, if you tried, make symbols for these. What if I put static here? This is a different static than the one I had earlier. Like, what does this static mean? Yeah, it means that this is basically like a local global kind of thing. It has static storage duration, so there's only one value in the entire execution of the program. So every time I call this function, it's the same value. So if I increment this by 1 every time I call the function, then each invocation is going to see an incremented value. So it's kind of like a global, but you just scoped inside of this function. So now who gets a symbol? Function, param, value. Function and value? Yep, that's correct, because now when I use value here, I need to be able to refer to the same value every time. It's just not something on the stack or in a register or whatever. I need to always get the same one. So it's like a singular thing in my program that I need to be able to access. So this value goes off in some of the data segments somewhere, and I need to find the right one every time. So then that's why I get a symbol for this one. But again, since I'm not modifying it in this example, like there's no modifications here, it could be inlined as well, and then you don't get the symbol. And yeah, it's also lowercase d here. It has internal linkage because like no one can access that from the outside. Yeah, I'll quickly mention this, and then I think we are nearing the end, so I'll have some time for questions. So just to summarize who gets a symbol, only things that there are one of, like the global or the function, they have to be one thing that you can link to. If a symbol has internal linkage and is inlined, it's not emitted. It's because then no one else will be able to use it. And the same, if you don't use a weak or unique symbol, you don't get the code for it. Right, so in summary, For the entire thing, we saw in the beginning that we have this separate compilation model, which and then you have relocations because the compiler doesn't know where things are. The linker will fill it in. That's why we have symbols, so the linker can fill in these things. External internal linkage maps to global and local binding on ELF. Weak and unique binding is used for symbols defined in headers to allow for the duplicates. For shared objects, you use visibility instead of binding, and you can control this with fVisibility or the attribute visibility. We saw we have this various sections: data section, text section, symtab, dinsim, and then rela is for relocations. And we can use nm, objump, and readelf to look at our binaries. And we can use strip to remove symbols. And finally, we saw that like only these singular things that there are one of actually get symbols. So you don't need symbols for locals and stuff. Yeah, here are links to this talk. Talks about like the assembly that of the kind that we're using here are like related to calling functions and stuff. And this one goes more into detail about linking. So that's it. Thanks for coming. I think we're exactly on time, but should we take one or two questions? Or is there a lowercase weak? I don't think so. I can't imagine a use case for it, because if it's weak, it's because you have to like disambiguate these things. But I'm not sure. I don't think so. One more question? No, I'll hang around here so you can come up and ask if you want as well. Thank you.